What is intuitionism?
There are some people within philosophy and mathematics who reject the formalism of mathematics and believe in intuitionism, which says that words and formulas have significance only as a reflection of the mind's activity. Intuitionists believe that a theorem is meaningful only if it represents a mental construction of a mathematical or logical entity. This is different from the classical approach that states that the existence of an entity can be proven by refuting its non-existence. For example, if you said A or B to an intuitionist, he or she believes that either A or B can be proved. But if you said, A or not A, this is not allowed. Since you cannot assume that it is always possible to either prove or disprove statement A.
Was Fermat's last theorem finally solved?
Just before the end of the 19th century, German industrialist and amateur mathematician Paul Wolfskehl, on the brink of suicide, began to explore a book on Fermat's last theorem. Enchanted with the numbers, he forgot about dying and instead believed that mathematics had saved him. To repay such a debt, he left 100,000 marks, about $2 million in today's money, to the Göttingen Academy of Science as a prize to anyone who could publish the complete proof of Fermat's last theorem. Announced in 1906 after Wolfskehl's death. Thousands of incorrect proofs were turned in, but no true proof was offered. But people kept trying and failing. Fermat's last theorem was finally solved in 1994 by English mathematician Andrew John Wiles, 1953. Wiles was offered the Wolfskehl Prize in 1997. By that time, the original $2 million had been affected by not only hyperinflation but also the devaluation of the mark, reducing its value to $50,000. But for Wiles, it didn't matter, his proving the last theorem had been a childhood dream. It is interesting to note that some mathematicians do not believe Wiles uncovered the true proof of Fermat's last theorem. Instead, because many of the mathematical techniques used by Wiles were developed within recent decades, some even by Wiles himself. Wiles's proof, although a masterpiece of mathematics, could not possibly be the same as Fermat's. Still, other mathematicians wonder about Fermat's words in claiming that he had found a proof.
What are some basic steps to building a mathematical model?
Just like building a physical structure, there are basic steps to building a mathematical model. The first steps are to simplify the assumptions, or to clearly state those assumptions on which the model will be based, including an understandable account of the relationships among the quantities to be analyzed. Second is to describe all the variables and parameters to be used in the model, and identify the initial conditions of the model. Finally, use step 1's assumptions and step 2's parameters and variables to derive mathematical equations.
When was the first arithmetic book published in North America?
In 1556 the first arithmetic book was published in North America by Brother Juan Díaz Fraile, a Franciscan friar. The name of the book was Sumario Compendioso de las Cuentas de Plata y Oro que en los Reinos del Peru. Son necesarias a los mercaderes y todo género de tratants, con algunas reglas tocantes al arithmética. The title translates as Comprehensive Summary of the Counting of Silver and Gold, which, in the kingdoms of Peru, are necessary for merchants and all kinds of traders. The book explained the conversion of gold ore into value equivalents in different types of coinage in the Old World. Problems that required the use of ratios and proportions. Diaz also included a short chapter on algebra. The first English-language mathematics book written in North America was published in 1729 by Isaac Greenwood and titled Arithmetic, Vulgar and Decimal. Vulgar refers to the common people. Greenwood's life was also somewhat vulgar. He was appointed to the first Hollis Professorship of Mathematics and Natural Philosophy at Harvard University in Massachusetts when it was founded in 1727. By 1737 he was removed for intemperance. Reportedly, he drank too much, and more than likely his views, philosophical and otherwise, differed greatly from those of his colleagues at the university.
The problem with this proof?
If x equals y, then xy equals 0. Notice that halfway through the proof, the equation was divided by xy, which makes the proof erroneous.
What are median and mode?
The median is considered half the sum of the two numbers nearest the middle. In other words, in an ordered data set, the median is the value at the halfway point, above and below which lie an equal number of data values. But note, there is an actual middle number for a set with an odd number of members, but no middle number for an even number of members. The mode is considered a single value that occurs more often than any other in a set of data. It is not the frequency of the most numerous number, but the value of the number itself. Often there is more than one mode if two or more values are commonly found in the set, often called a multimodal population.
What is the golden ratio?
The golden ratio, also known as extreme and mean ratio, golden section, golden mean, or divine proportion, is a number that has many interesting properties. It is associated with the balance between symmetry and asymmetry used in art and design. Two quantities are said to be in the golden ratio if the whole is to the larger as the larger is to the smaller. Euclid expressed it as, a straight line is said to have been cut in extreme and mean ratio when, as the whole line is to the greater segment, so is the greater to the less. This is seen in the accompanying illustration, in which for two segments A and B, the entire line is to the A segment as A is to the B segment.
For what other invention was John Napier known?
Scottish mathematician John Napier may have been known for his contributions to logarithms. But he was also the inventor of a tool called Napier's bones, also known as Napier's rods. These were multiplication tables inscribed on strips of animal bone or wood. Wilhelm Schickard would eventually build the first calculating machine based on Napier's bones. A device that could add, subtract, and with help multiply or divide. Napier was also the instigator in another discovery, in 1621 English mathematician and clergyman William Oughtred. 1575 to 1660, used Napier's logarithms as the basis for the slide rule. A ruler-like instrument used long before handheld calculators came into vogue. Oughtred not only invented the standard rectilinear slide rule, but also the circular slide rule, which was an extremely useful tool that remained in common usage for more than 300 years. For more about Oughtred, see Math Basics.
Who were some of the most influential Ionian, Greek, and Hellenic mathematicians?
The Ionians, Greeks, and Hellenics had some of the most progressive mathematicians of their time, including such mathematicians as Heron of Alexandria, Zeno of Elea, Eudoxus of Cnidus, Hippocrates of Chios, and Pappus. The following are only a few of the more influential mathematicians. Thales of Miletus, c. 625 c. 550 BCE, Ionian, besides being purportedly the founder of a philosophy school and the first recorded Western philosopher known, made great contributions to Greek mathematics, especially by presenting Babylonian mathematics to the Greek culture. His travels as a merchant undoubtedly exposed him to the geometry involved in measurement. Such concepts eventually helped him to introduce geometry to Greece, solving such problems as the height of the pyramids, using shadows, the distance of ships from a shoreline, and reportedly predicting a solar eclipse. Hipparchus of Rhodes, c. 170 c. 125 BCE, Greek, also seen as Hipparchus of Nicaea, was an astronomer and mathematician who is credited with creating some of the basics of trigonometry. This helped immensely in his astronomical studies, including the determination of the moon's distance from the Earth. Claudius Ptolemaeus, or Ptolemy, c. 100–c. 170, Hellenic, was one of the most influential Greeks. Not only in the field of astronomy, but also in geometry and cartography. Basing his works on Hipparchus, Ptolemy developed the idea of epicecles in which each planet revolves in a circular orbit, and each goes around an Earth-centered universe. The Ptolemy way of explaining the solar system which we now know is incorrect. Dominated astronomy for more than 1,000 years. Diophantus, c. 210–c. 290, was considered by some scholars to be the father of algebra. In his treatise Arithmetica, he solved equations in several variables for integral solutions, or what we call Diophantine equations today. For more about these equations, see algebra. He also calculated negative numbers as solutions to some equations, but he considered such answers absurd.
What are the modern connections between architecture and mathematics?
The foundations of modern architecture began with mathematics. Mathematical planning goes into creating almost every working, freestanding structure. From the smallest monument to the tallest buildings and bridges. For example, in order to build a structure, the area where the building will be erected must be measured to see if it will fit. Measurements and surveys, then the building plans need to be drawn up in scale drawings made proportionally smaller to the structure's real size. For more information, see below, and the amount of building material must be estimated, mathematics to figure out the budget. Finally, the actual structure must be built to specifications so the building will stand without collapsing, geometry and measurement.
How does one calculate heart rate during exercise?
One reason to calculate heart rate during exercise is to know if a person is getting beneficial exercise to keep the heart and body healthy. In order to determine the safe and effective range of exercise to get cardiovascular benefits, two measurements are often taken. The first is the maximal heart rate, a number related to a person's age. The heart beats slower with age. To estimate the maximal heart rate, subtract a person's age from the number 220. For example, if someone is 40 years old, his or her maximal heart rate is 180. The next measurement is the target heart rate zone. This number uses the maximal heart rate and represents the number of times per minute at which a heart should be beating during aerobic exercise. For most healthy people, the range is 50% at the lower limit to 80, some charts say 75% at the upper limit of their maximal heart rate. When a person's heart rate reaches a value within this zone during exercise, it means he or she has achieved a level of activity that contributes to his or her cardiovascular fitness. For instance, from the above example of a maximal heart rate of 180, the beats per minute. For the lower range would be 180 multiplied by 50%, 0.50, or 90 beats per minute. The upper range would be 180 multiplied by 80%, 0.80, or 144 beats per minute. If you work out and maintain a lower than 50 or higher than 80% limit, there are few beneficial effects from the exercise. In terms of the lower limit, the heart is not working hard enough for any cardiovascular benefit. In terms of the upper limit, besides the strain and injuries that can result, the heart is working too fast for any benefit and the body can't replenish oxygen that quickly.
What do the numbers on an aneroid barometer signify?
The non-liquid aneroid barometer measures air pressure. As the atmospheric pressure changes because of storm systems or lack of storms, the instrument records the changes. Because atmospheric pressure changes with distance above or below sea level, a barometer can also be used to measure altitude. The aneroid barometer contains a small capsule that acts like a bellows, but with the air removed. When the air pressure increases, the sides of the capsule are pushed in and the connected needle rises, moves clockwise. When the air pressure decreases or falls, the capsule's sides puff out and the needle moves in a counterclockwise direction. The numbers on a common barometer range from about 26 to 31, with divisions of 10 or more in between each number. A needle, actually a hand similar to a clock hand, points to the numbers on the barometer and moves in response to the changing air pressure. These numbers are based on the principle that atmospheric pressure supports 30 inches. 76.2 centimeters, of liquid mercury in a tube with one end sealed. And this information is based on the mercury barometer, the first type ever made.
What does the word parallel mean in geometry?
In geometry, parallel means two lines in two-dimensional Euclidean space that do not intersect, or two lines in the same plane that never meet and that maintain the same distance from each other at every point. In three-dimensional Euclidean space, these lines also do not intersect, maintaining a constant separation between points closest to each other on the two lines. In analytic geometry, parallel means those lines with the same slope, as well as other curves with the same slope for every x value. The symbol for parallel lines is. For example, AB means that line A is parallel to line B.
What are astronomy and astrophysics?
Astronomy is the study of matter in outer space. It is usually considered a branch of physics. But because it encompasses, literally, an astronomical number of subjects, everything from the study of a star's surface to the end of the universe, it is often considered a field of its own. Astrophysics is a branch of astronomy dealing with the physics of celestial bodies and the universe as a whole. It deals with problems that range from the structure, distribution, evolution, and interaction of stars and galaxies to the orbital mechanics of a near-Earth asteroid.
What is a finite element analysis?
A finite element analysis, also known as FEA or finite element method, is a powerful tool to solve problems in engineering, especially for heat transfer, fluid mechanics, and mechanical system problems. The FEA consists of a computer model of a material or design that is stressed. The outcome is then analyzed for specific results. In reality, the computer is conducting a numerical analysis technique used for solving differential equations and relating it to stress in the engineering problem. This technique was first developed in 1943 by Richard Courant, 1888 to 1972. Who used a form of FEA to find approximate solutions to vibrational systems. Early in the 1970s, only companies that owned expensive mainframe computers were using FEA, including the aeronautic, automotive, defense, and nuclear industries. Since the mid-1990s, however, use of FEA has grown with the advent of faster and cheaper computers with more memory. The results are more accurate, too, allowing various industries to analyze new product designs and refine existing products.
How are equations with exponents and logarithms solved?
The way to solve an exponential equation is relatively easy. Take the log of both sides of the equation, then solve for the variable. For example, to solve for x in the equation x equals 60, first, take the natural log, ln, of both sides. ln, x, equals ln, 60, simplify using the logarithmic rule number 3, see above, for the left side, x ln, e equals ln, 60, then simplify again, since ln, e, equals 1 to, x equals ln, 60, equals 4.09434456 and finally, check your answer. Using log tables or your calculator, in the original equation x equals 60, e 4.09434456 equals 60 is definitely true. The way to solve a logarithmic equation is equally easy. Just rewrite the equation in exponential form and solve for the variable. For example, to solve for x in the equation ln, x, equals 11, first, change both sides so they are exponents of the base e. ln, x, equals e11 when the bases of the exponent and logarithm are the same. the left part of the equation becomes x, thus, it can be written, x equals E11 to obtain x. Determine the solution for E11, or x is approximately 59,874.14172. And finally, check your answer. Using tables or your calculator, in the original equation ln, x, equals 11, ln, 59,874.14172, equals 11 is definitely true.
What are the arithmetic mean and geometric mean?
The average, in general, means the average value of a group of numerical observations or the statistical measure of the arithmetic mean, or just the mean. On a scale of measurement, it is usually the place in which the population is centered. Numerically, it equals the sum of the scores divided by the number of scores. For example, the sum of 3, 7, 10, 15, and 25 is 60, thus, the mean is 60 divided by 5, or 12. The geometric mean is another type of mean. For two quantities, it is the square root of the quantities' product. The notation is for n quantities, and the geometric mean is the nth root of their product.
What are the measures of central tendency?
The measures of central tendency are statistics that describe the grouping of values in a data set around a common value that in some way represents a typical member. They are broken down into four types: median, mode, average. Also called the arithmetic mean, and the geometric mean.
What are the common types of mathematical operations?
Operations are ways to obtain a single entity from one or more entities by manipulating numbers and letters, in certain ways. They include the elementary operations most of us are familiar with: addition, subtraction, multiplication, division, cubing, squaring, and integer root extraction. There are numerous types of other operations, too, including binary operations, in which two quantities or expressions x and y interact in set theory. For more about set theory, see Foundations of Mathematics.
What are other types of angles?
There are numerous other types of angles, some of which are examined in the following list. Adjacent angle. Adjacent angles are two angles side by side that have a common vertex, endpoint, and ray. Angles are adjacent if a common line is between the other sides. Vertical angles. Vertical angles are two angles whose sides form two pairs of opposite rays. Because of this, vertical angles have no sides in common and are directly across from one another. They are also considered a pair of opposite congruent angles where two lines intersect. Vertical angles include intersecting lines that define a plane. With the vertical angles always in the same plane. Congruent angles have the same size and shape. Vertical angles are considered to be congruent. Exterior and interior angles are those inside a polygon, such as a triangle. Exterior angles are outside the polygon formed by extending one ray, side, outside the polygon from a vertex. Alternate and corresponding angles, a pair of angles that lie on opposite sides and opposite ends of a transversal. A line that cuts two or more lines in the same plane are called alternate angles. Both these angles are equal if the lines cut by the transversal are parallel. They are also broken into alternate interior angles, the inside angles, and alternate exterior angles, the outside angles. For two parallel lines, the alternate interior and exterior angles are equal or congruent. Corresponding angles are pairs of angles that lie on the same sides and ends of a transversal. Dihedral angle, a dihedral, meaning two bases. Angle is one of the four angles formed where two non-parallel planes meet. Complementary angles, two angles that add up to a right angle are complementary. For example, the two acute angles in a right triangle are always considered complementary. As their sum adds up to 90 degrees of the right triangle. Supplementary angles, two angles that add up to a straight angle, 180 degrees, are supplementary. If the angles are both supplementary to the same angle, then the two angles are congruent.
What is mathematical physics?
Mathematical physics uses the concepts of statistical mechanics and quantum field theory. But it is not the same as theoretical physics. Mathematical physics studies physics on a more abstract and meticulous level. Theoretical physics entails less mathematics than mathematical physics and has more to do with experimental physics. But like many fields of science, defining mathematical physics is not easy. For example, still another definition of modern mathematical physics states that it entails all areas of mathematics other than classical mathematical physics.
How is math used to understand chemical reactions?
One of the simplest examples of mathematics used in understanding chemical reactions is based on two chemicals, A and B. They can be molecules or ions. If A and B encounter one another, they can rearrange themselves into molecules or ions of two other substances, in this example, C and D. The reaction that takes place can give off or absorb energy, making the molecules move faster or slower. Although this is a simple example of what can happen in a chemical reaction, it can still be analyzed using mathematical modeling.
How are some stock market financial indicators calculated?
There are numerous financial indicators associated with the stock market, and they all have to do with mathematical calculations. Dividends are taxable payments put forth by a company's board of directors and distributed to its shareholders. These monies come from the company's current or retained earnings and are usually paid out every quarter. They can be either in the form of a cash dividend, usually in check form, stock dividend, or other property. The dividend yield is the yield paid out by a company to shareholders in the form of dividends, calculated by the amount of dividends paid per share over a year, then divided by the stock's price. For example, if a stock pays out $2 in dividends over the course of a year and trades at $40, the dividend yield is 5%. The P/E ratio stands for price/earnings ratio, a measure of a stock's amount to its earnings per share. It is a measure of a stock's market capitalization, divided by its after-tax earnings over a 12-month period. The higher the P/E ratio, the more the market is willing to pay for each dollar of annual earnings. Of course, companies with negative earnings, or those that are not profitable, have no P/E ratio at all.
What Greek mathematician wrote the book Elements?
The Greek mathematician and geometrician Euclid, c. 325–270 BCE, made some of the most significant improvements to geometry in his time. For more about Euclid, see History of Mathematics and Foundations of Mathematics. One contribution was his collection of 13 books on geometry and other mathematics, titled Elements, or Stoicheion in Greek. This work has been called the world's most definitive text on geometry. The first 6 books offer elementary plane geometry, with sections on triangles, rectangles, circles, polygons, proportions, and similarities. The rest of the books present other mathematics of his day, including the theory of numbers, books 7 to 10, solid geometry, pyramids, and Platonic solids. These books were used for centuries in Western Europe, in fact. The elementary geometry many students learn in high school today is still largely based on Euclid's ideas on the subject.
What is relativity?
Relativity refers to the idea that the velocity of an object can be determined only relative to the observer. For example, if a fly moves around the inside of a car at about 1 mile per hour, inside the car's frame of reference, the fly is moving at 1 mile per hour. But if the car goes past you at 65 miles per hour, it will appear as if the fly is traveling at 66 miles per hour, not 1 mile per hour. In other words, it's all a matter of reference, and it's relative to your viewpoint.
What does the term statistically significant mean?
For most of us, significant means important. In statistics it means probably true, not due to chance, but not necessarily important. In particular, significance levels in statistics show how likely a result is due to chance. The most common level one thought to make it good enough to believe is 0.95. Which means the finding has a 95% chance of being true. This can also be misleading, however. No statistical report will indicate a 95%, or 0.95, in its answer. But it will show the number 0.05. Thus, statisticians say the results in a backward manner. They say that a finding has a 5% chance of not being true. To find the significance level, all one has to do is subtract the number shown from 1. For example, a value of 0.05 means that there is a 95%, 1. 0.5 equals 0.95, chance of it being true. For a value of 0.01, there is a 99% chance. 0.01 equals 0.99, of it being true, and so on. Bar graphs are similar to histograms, but with the columns separated by each other by small distances. They are commonly used for qualitative variables. A pie chart is another way to represent data graphically. In this case, it is a circle divided into segments, or pie wedges. Each segment represents not only a certain category, but its proportion to the total set of data. Another type of graph is the line graph, which is similar to those seen in geometry. A representation of the data from connected point to connected point. They are one of the most common graphs seen for simple statistical data collection.
How are some common solids defined?
There are numerous objects defined in solid geometry. The following lists the most common, and some interesting ones. Cone. A cone can be both a surface and a solid. A solid cone is bounded by a region enclosed in a closed curve on a plane and a surface, formed by segments joining each point of the closed curve to a point that is not in the plane. Note, two solid cones seen with their pointed ends together help define conic sections. For more about conic sections, see elsewhere in this chapter. Pyramid. A pyramid is a polyhedron, see above. With one face a polygon and all other faces as triangles with a common endpoint, vertex. They are named based on the polygon's base, such as the triangular pyramid, square pyramid, and so on. Some of the most famous solid pyramids are the sandstone pyramids of Egypt. These are actually called right square pyramids because the base of the polygon is a square and the vertical line from the vertex meets the center of the base. Cylinder. A cylinder can be both a surface and a solid. A solid cylinder is one that forms by rotating a circle about an axis through the midpoints of the opposite side. It is also called a right circular cylinder. One of the most well-known cylinders is possibly sitting right next to you, a coffee cup. With its cylindrical shape, and the bases, in this case, the base and rim, considered to be congruent circles. Prism. A prism is a polyhedron with two parallel, congruent faces that make up the bases of the shape. The other, lateral faces are considered to be parallelograms. If the lateral faces are rectangles, the prism is called a right prism. Parallelepiped. This strange-sounding polyhedron is one that has all its faces as parallelograms, or a prism with parallelogram bases. The most familiar parallelepiped is a simple box, also called a rectangular parallelepiped that has rectangles for all the 6 faces. For more about these figures, including how to calculate their areas, see elsewhere in this chapter.
In what way do some historians link mathematics to the pyramids?
The pyramids in Egypt were built as royal tombs for the pharaohs, first along the edges of cliffs as low rectangular structures called mastabas, then as tall, four-sided pyramids. The 3 structures most of us associate with pyramids were built at Giza, near Cairo, about 2500 BCE. The largest of these, the Great Pyramid of the Pharaoh Cheops, measures 481 feet, 147 meters, high. But there are no intricate pathways in this pyramid. It is merely a pile of limestone blocks weighing between 3 and 15 tons.
What is a Diophantine equation?
The first mention of Diophantine equations was by Greek, Hellenic, mathematician Diophantus, c. 210 c. 290 CE. In his treatise Arithmetica. He solved equations with several variables for integral solutions, what we call Diophantine equations today. For more about Diophantus in history, see History of Mathematics. These are represented by one equation with at least 2 variables, such as x and y, and whose solutions have to be whole numbers, or integers. These equations either have no solutions, or an infinite or finite number of solutions. Diophantine analysis is the mathematical term for how to determine integer solutions for such algebraic equations.
How do you add matrices?
It is pretty easy to add matrices. For example, for 1 2 plus minus 1 minus 2, you add the matrices, or in this case, row numbers, simply by adding the corresponding terms in each matrix. Thus, the matrix of 1 2, plus, minus 1 minus 2, equals, 1 to 1 2 to 2, equals, 0 0. All that remains of the once great Maya civilization are remarkable ruins such as these in the Yucatan Peninsula of Mexico. They are reminders of an advanced culture that had made great strides in mathematics, including the use of matrices, the image bank/Getty images.
What are equations?
In its simplest form, an equation is represented by expressions written with an equal sign in between. The two entities on either side are equal to each other. They are among the simplest mathematical problems most people deal with. Most people have solved equations in their daily lives without realizing it. For example, when students first learn addition in school, they typically work on equations such as, plus 5 equals 7, in which the blank needs to be filled. This problem could also be expressed as x plus 5 equals 7, a simple equation. In this case, the equation is solved when x equals 2. The following are also equations. 6 equals 6x equals 8y plus 8 equals 14x 4 equals 15x 5xy equals 8xy 2 plus 4. There are also some fundamental properties of equations that are good to know. They include symmetric properties. If A equals B, then B equals A, substitution, if A equals B, then A may be replaced by B, addition, if A equals B, and C is a number, then A plus C equals B plus C, and multiplication, if A equals B, and C is a number, then AXC equals BXC.
What are the major scales used in interpreting hurricanes and tornadoes?
There are two major scales used to interpret hurricane and tornado intensity and thus potential damage. The Saffir-Simpson Hurricane Damage Potential Scale is a hurricane force scale using the numbers 1 through 5 to rate a hurricane's intensity. The scale was developed by engineer Herbert Saffir, 1917, and pioneer hurricane expert Robert Simpson. 1912, in 1971. A number on the scale is assigned to a hurricane based on its peak wind speed. It is also used to give an estimate of the potential property damage and flooding expected along the coast from a hurricane landfall. The Fujita-Pearson Tornado Intensity Scale, or F-scale, is used to measure tornado wind speeds. It was developed in 1971 and named after Tetsuya Theodore Fujita, 1920 to 1998, of the University of Chicago, and Alan Pearson, who was then head of the National Severe Storms Forecast Center in Kansas City. It was Fujita who came up with a system to rank tornadoes according to how much damage they cause. He developed his categories by connecting the 12 forces of the Beaufort wind scale. Knots based on what the sea surface looks like from smooth to waves over 45 feet, with the speed of sound, Mach 1. Then, For each category he estimated how strong the wind must be to cause certain observed damages. Fujita's scale was later combined with Pearson's scale, which measures the length and width of a tornado's path, or its contact with the ground.
Did any cultures use more than one base number in their numbering system?
Certain cultures may have used a particular base as their dominant numbering system, such as the Sumerians' base 60, but that doesn't mean they didn't use other base numbers. For example, the Sumerians, Assyrians, and Babylonians used base 12, mostly for use in their measurements. In addition, the Mesopotamian day was broken into 12 equal parts. They also divided the circle, ecliptic, and zodiac into 12 sections of 30 degrees each.
What is a Fourier series?
The idea for the Fourier series was developed by French mathematician and physicist Baron Jean-Baptiste Joseph Fourier. 1768 to 1830, as an alternate method of expressing a function by the expansion of the function. A Fourier series is actually a specific type of infinite mathematical series that involves trigonomic functions. More simply put, it is essentially an infinite sum of sine waves. The Fourier series is used in applied mathematics. In engineering and physics, it is used to split up a periodic, or continuous, function into a group of simpler terms. In electronics, it is used to express the periodic function seen in waveforms of communication signals.
What mathematical measurement error once occurred when a spacecraft reached Mars?
The Mars Climate Orbiter spacecraft, a joint effort between Lockheed Martin and NASA's Jet Propulsion Laboratory, JPL, was supposed to go into orbit around the red planet on September 23, 1999. Instead, the Martian craft lost all contact with Earth. After much deliberation, a review panel for the incident came to a disconcerting conclusion. A thruster error developed when project teams used different measuring systems for the navigation commands. NASA used metric units. Lockheed Martin used English Standard Units, and no one caught the discrepancy. To this day, scientists can only speculate as to what happened to the orbiter. A craft sent to study the climate and weather patterns of the Martian atmosphere. Some say that because the orbiter dropped down to within 36 miles, 60 kilometers, of the planet, about 62 miles, 100 kilometers, closer than planned, atmospheric friction probably overheated the propulsion system and tore the vehicle apart. Others believe the craft was propelled through the atmosphere, or bounced off and out into space again, and is now perhaps circling the sun like an artificial comet.
What are examples of polynomials with one root and no roots?
The following is an example of a polynomial with only one root: x2 plus 6x plus 9 equals 0, x2 plus 6x plus 6 halves, 2, 6 halves, 2 plus 9 equals 0, x plus 3, 2 9 plus 9 equals 0, x plus 3, 2 equals 0, x plus 3 equals 0, x equals minus 3. Or the polynomial has only one root, x equals minus 3, but not all polynomials have roots. The following is an example of a polynomial with no root: 2x2 6x plus 8 equals 0, 1 half, 2x2 6x plus 8, equals 1 half, 0x2 3x plus 4 equals 0, x2 3x plus, minus 3 halves, 2, minus 3 halves, 2 plus 4 equals 0, x 3 halves, 2 9/4 plus 4 equals 0, x 3 halves, 2 plus 7/4 equals 0, x 3 halves, 2 equals minus 7/4, because a real number squared is greater than or equal to 0, that means, x 3 halves, 2 will always be greater than or equal to 0. Thus, the answer can't be minus 7/4, a negative number, and there are no real roots for this polynomial.
In what ways does mathematics apply to music?
There are many ways in which mathematics applies to music, from harmonics to the concept of octaves and scales. There is a most interesting connection in that both music and mathematics are experienced as pure objects of the brain, and both have meaning outside of the brain only through artificial connections. For example, there is a mathematical reason why certain note combinations sound harmonious to most people. One good example is a violin string. When it is plucked, the string vibrates back and forth, creating mechanical energy that travels through the air as wave patterns. The number of times the waves reach a person's ear is called the frequency, which is measured in hertz, or cycles per second. If more waves are heard within a certain time period, the note's pitch sounds higher. Chords sound harmonious to us because of waves and ratios. For example, take the C major chord, in which the note middle C is 261.6 Hz. The note E is 329.6 Hz, and the note G is 392.0 Hz. The ratio of E to C is about 5/4, or every fifth frequency wave of E matches with every fourth wave of C. The ratio of G to E is also about 5/4, and the ratio of G to C is about 3/2. Because the notes' frequencies match with the other notes' frequencies, they all sound harmonious to a person's ear. It is interesting to note that none of the ratios for the familiar Western-style scale are truly exact, but rather are approximations. This is because when this scale was put together, the creators wanted to make the notes go up in equal intervals and the ratios to be in tune. The only way to do this was to compromise and use inexact ratios.
What are imaginary numbers?
The opposite of real numbers are, logically enough, called imaginary numbers. If you square a positive number, the result is positive. If you square a negative number, the result is also a positive number. Thus, in order to square a number to get a negative one, mathematicians invented the imaginary number, I.
What are tiling and dissection puzzles?
Tiling puzzles are two-dimensional shapes that are reassembled into a larger given shape without overlaps. The best examples of these are dissection puzzles. The most common ones are those in which an object is converted to another by making a finite number of cuts, then reassembling the pieces. Most of the cuts are represented by straight lines, but not always. In addition, sometimes the cut object can be reassembled into two or more shapes.
What is statistical quality control?
Quality control has been around for a while in a crude sense. When a certain product was manufactured, and consumers chose that product, the makers would try to improve the quality of the product or lower its price. The improvement of the quality did not stop with the product, but also included the process for making the product. But the use of mathematics was minor in early quality control. It was not until the 1920s that statistics was applied to industry and quality control. Mainly because of the development of sampling theory. For more about sampling, see Applied Mathematics. Modern statistical quality control refers to using statistical techniques for measuring and improving the quality of processes. It is often broken down into statistical process control, SPC, see above, and statistical quality control, SQC. Both terms are usually used interchangeably, although SQC has a broader focus than SPC. To compare, SPC is the application of statistical techniques to control a process, reducing variation so that performance remains within specific limits. SQC is the application of statistical techniques to control quality and includes acceptance sampling, inspection of a sample from a lot to decide whether to accept that lot, as well as SPC.
Is measurement tied to mathematics?
Yes, measurement is definitely tied to mathematics. In particular, the first steps toward mathematics was using units, and eventually numbers, to describe physical quantities. There had to be a way to add and subtract the quantities. And most of those crude calculations were based on fundamental mathematics. For example, in order to trade horses for gold, merchants had to agree on how much a certain amount of gold, usually as weight, was worth, then translate that weight measurement into their barter system. In other words, X amount of gold would equal Y amount of horses.
What is an angstrom?
An angstrom, A, is a unit of measurement often used in chemistry, most often in reference to molecules. For example, the average molecule diameter is between 0.5 to 2.5 angstroms. An angstrom is equal to about 3.937 x 10 to 9 inch or 1/100th of a millionth of a centimeter, 10 to 8 centimeter. For more information about measurement, see Mathematics in History.
What are some examples of Venn diagrams?
Venn diagrams are schematic illustrations used in logic theory to show collections of sets and the relationship between them. Overlapping circles represent the sets, or the subjects and predicates in syllogistic logic. The standard way of presenting such diagrams include the intersection of two. Order 2 diagram, to 3, order 3 diagram, circles. Based on what circles intersect and the areas shaded. A conclusion about the sets may then be read directly from the diagram. Such illustrations can include the union of two sets, the intersection of two sets, the complement of a set, and the complement of the union of two sets.
How did the concept of zero evolve over time?
The concept of zero developed because it was necessary to have a placeholder or a number that holds a place to make it easier to designate numbers in the tens, hundreds, thousands, etc. For example, the number 4000 implies that the 3 places to the right of the 4 are empty with only the thousandths column containing any value. Because 0 technically means nothing. At first few people accepted the concept of nothing between numbers. Not that all cultures ignored the possibility of such an idea. For example, Hindu mathematicians, who wrote their math in verse, used words similar to nothing, such as sunya, void, and akasa, space. It is thought that the Babylonians were the first to have a placeholder in their numbering system, but not a zero. Instead, it appears they used other symbols, such as a double hash mark, also called wedges, as a placeholder. Archaeologists believe a crude symbol for zero probably started in Indochina or India about the 7th century and by the Mayans independently about 100 years earlier. While the isolated Mayans could not spread the idea of the zero, the Indians seemed to have no problem. Around 650 CE, zero became a mathematically important number in Indian mathematics, although the symbol was a bit different than today's 0. The familiar Hindu Arabic symbol for 0, the open circle, would take several more centuries to become more readily accepted. For more about 0 and Hindu Arabic symbols, see History of Mathematics and Math Basics.
What are the two ways of looking at the derivative?
There are two major ways of looking at the derivative: the geometrical, or the slope of a curve, and the physical, the rate of change.
How did the metric system originate?
In 1791, the French Revolution was in full swing when the metric system was proposed as a much-needed plan to bring order to the many conflicting systems of weights and measures used throughout Europe. It would eventually replace all the traditional units, except those for time and angle measurements. The system was adopted by the French Revolutionary Assembly in 1795, and the standard meter, the first metric standard, was adopted in 1799. But not everyone agreed with the metric system's use, and it took several decades before many European governments adopted the system. By 1820, Belgium, the Netherlands, and Luxembourg all required the use of the metric system. France, the originator of the system and its standards, took longer, finally making metric mandatory in 1837. Other countries such as Sweden were even slower. They accepted the system by 1878 and took another 10 years to change from the old method to the metric.
What are ordinal and cardinal numbers?
In common, arithmetic terms, cardinal numbers are those that express amounts. They are also used in simple counting or to answer the question of quantity, how many. They can be nouns, try counting to 10, as pronouns, 10 were discovered, or adjectives, 10 cats. Specifically, the term is from the Latin cardine, meaning stem or hinge, referring to the most important or principal numbers, with others depending, hinging, on those numbers. We are most familiar with the cardinal numbers as our counting numbers, or the Hindu Arabic numeration system 1, 2, 3, and so on. Ordinal numbers are much different. In common, arithmetic terms, ordinal numbers are adjectives that describe the numerical position of an object, such as first, second, third, and so on. They are used to show the order of succession for objects, second chair, names, second month, or periods of time, second century. Note that cardinal and ordinal numbers are easily divided. For example, in the Hindu Arabic numeration system, the cardinal numbers may be read as ordinals, such as May 10th being read as May 10th. Such differences are even harder to distinguish when it comes to Roman numerals. Most of the time, these numerals are considered cardinal numbers, I, 2, 3, etc. But they can also be ordinal numbers in certain contexts, such as Henry VIII, Henry VIII. Roman numerals can even contain ordinal suffixes, such as the IXTH dynasty.
What are scale drawings?
Scale drawings are drawings or illustrations that are proportional in scale to the real structures they represent. In order for a new building to be designed, an architect must convert his or her ideas to drawings. But since the drawings can't be as large as the building, the architect uses scale drawings to depict the structure. These miniature versions of the actual structure show the sizes, shapes, and arrangements of rooms. Along with structural parts, windows, doors, closets, and other important details of construction. The scale drawings of these buildings must be in exact proportion to the actual structure, with various scales used for this purpose. For example, 1/8 inch might be used to represent 1 foot, thus, an 8-foot long building feature would be drawn as an inch long on paper. One of the most common scales used by architects is 1/4 inch equals 1 foot. These measurements can also be translated into the metric scale. Scale drawings are also used in other engineering fields, such as surveying. For example, distances measured in the field can be translated to a smaller scale, such as a drawing, in order to accurately depict what was measured. The ratio between the real distance and the drawn distance is called the drawing scale. If the measurement is 200 feet in the field and on paper the desired line is 8 inches long, then 8 inches on the paper would equal 200 feet on the ground, and 1 inch would be equal to 25 feet on the ground. This is translated as a diagram with a scale of 1 equals 25, 1 inch equals 25 feet, or 125. There is another way of approaching such an illustration. If the longest distance measured in the field was 300 feet and the desired drawing scale is 1 inch equals 25 feet, then the minimum length of paper needed would be 12 inches, or 300/25.
What is the annual percentage rate, or APR?
The annual percentage rate, APR, is an expression of the yearly interest rate that will be paid on a loan, which includes credit cards. It differs from the advertised interest rate, as it includes one-time fees in an attempt to calculate the total cost of borrowing the money. Therefore, it is wise to always look for a low APR. Because lenders are required to disclose the APR before a loan or credit application is finalized, it makes it easier to compare lenders. For example, if a person borrows $100 for 1 year at 5% simple interest, they will owe $105 at the end of the year, and the lender charges a $5 fee. The total cost to borrow the money will actually be $10, meaning the APR is 10%.